Okay, Assalamualaikum warahmatullahi wabarakatuh. So we're going to continue with the inverter topic. So again, this is the session, the outcome of the session, which is after completing the session, the student should be able to describe the operation of inverter, derive the quantities related to the performance of inverter, solve problems related to inverter, and finally you'll be able to simulate inverter circuit using PSIM, inshallah. Okay, so let's look at what is the I've already please download the notes from the Padlet. Okay, so the switch mode inverter, the name is also known as a switch mode inverter. As we all know, that switch mode inverter is used to convert the DC input to the AC output. The common application is the solar PV system, whereby the inverters convert the DC voltage produced by the solar panel to AC voltage to suit the AC load requirement. Okay, so in this EPO 510, we're going to discuss on two types of inverter, which is a single phase inverter and three phase inverter. All right, and the single phase inverter could generate three types of output waveforms. Again, in this EPO 510, we only discuss on the three types of output waveforms, which is the square wave. We have learned this during our rectifier. So the output AC voltage will be in the form of square wave, quasi square wave, and finally we have another sinusoidal PWM waveform, pulse width modulations. I think you have learned this during communications as a subject, because where we have this pulse width modulation type of signals. And the topology, the circuit that we're going to discuss, consists of half bridge, and we have another full bridge topology. Okay, and for the three-phase inverter, there will be again three types of output waveforms. The first one is known as 120-degree conduction mode. The second one will be the 180-degree conduction mode, and the final one will be the same sinusoidal pulse width modulated signal output waveforms. Okay, so again, this is a DC. So the ideal DC voltage will be a constant, isn't it? A constant voltage, and then the output is a periodical waveforms. Periodic, it has a period. There is a frequency of the output. Okay, so mainly we have a 50 Hertz frequency. So in Malaysia we have this 50 Hertz frequency. So that will be the fundamental frequency that we're going to obtain. Alright, so let's have a look at a single phase inverter. The first topology that we're going to discuss is the half bridge. So if you look at the half bridge, it will consist of only two. Okay, so if you look at this, we only have okay, it is known as a half bridge because you only utilize two devices, one S1 and S2, and for the other legs, we call this as a leg 1, leg 2. Okay, so the first leg or the second leg, whatever it is, so one of the leg will consist of two switches, S1, S2, and these switches will be a high switching frequency type of switch, which can be MOSFET or the BJT or IGBT. Okay, you can use these two switches, and then the other leg. Okay, so let's name it as a leg 1. This is leg 2. Okay, for the other leg, you're going to utilize capacitor. So the capacitor have a very large capacitor there. All right, so this is known as a half bridge. Okay, so if the second topology that we're going to discuss is the full bridge. Okay, whereby you're going to replace this capacitor with another MOSFET. Right, so there is no capacitor in the circuit, and both legs have the switches. So all components are switches, right? Which is MOSFET or IGBT. So this is known as full bridge if we have all our switches. Okay, for the first topology, we're going to discuss on the half bridge topology, and then the full bridge is only twice of what we're going to have in the half bridge, 2 times of whatever voltage that you're going to get for the half bridge. Okay, so the first control or the first output that we're going to have is a square wave output. So how we're going to control the switch such that the output will be in terms of square waveform. So to be able for you to obtain a square waveform, you're going to switch on switch 1 from 0 to 180 degree, and for 100 to 180 degree to 360 degree, you're going to trigger S2. Right? So whenever S1 on, let's look at the flow of the current. Whenever switch 1 is on, the current will flow through S1, and then it will go into S2, will be off, isn't it? So it will appear as a short circuit here, and this will appear as a open circuit. Right? So the current will flow through S1, goes to the load. So this is your load, and then we will come back to the capacitor 2, charging the capacitor 2 up to half of the input voltage. Okay, so it will charge the capacitor to the half of the input, whatever input voltage that you have. If you have 100 volt, so there will be a 50 volt across the capacitor 2, right? And then come back to the negative terminals. So that will be the flow for when the switch 1 is on, and whenever switch 2 is on, the power flow will be from the source, and then it will go to C1, charge the capacitor 1 up to the half of the input voltage, which is 50 volt in this case, in this example, and then come back to that load. So now it will be negative, isn't it? It will be negative, and then you flow to your switch 2, because switch 2 is on, switch 1 is off, so you will flow through the switch 1, then come back to this terminal, negative terminal. Okay, so to look into what will be the output voltage, let's look at the waveforms. Okay, so here you're going to turn on switch 1. Okay, you're going to turn on switch 1 from 0 to 180 degree, and then you're going to switch on switch 2 from 180 degree to 360 degree. Okay, so during this time, S1 is off, and during this time you're going to see S2 is off, isn't it? Okay, so whenever switch 1 is on, voltage here will be what? So if you redraw the circuit during S1 is on, going to have that one, then it goes to that, then it pass to the load, they come back to C2, and C2 here is charged up to half of the E. So let's say this is E, and now you have half of the input voltage across that, and therefore if you look this equivalent circuits, your V load, V out will be equals to what? You have half of this across imposed across the capacitor, therefore across V out will be another half of E, isn't it? That will be half of the input voltage, right? So that will be the voltage here. Okay, so if this 100 volt, then you're going to see the peak voltage here, the amplitude will be 50 volt there, right? During the negative, during S2 is on, okay, wherever S2 is on, so in this case S2 is on, S2 is on, S1 is off, therefore you're going to have this circuit. Come back to C1, then negative, and short circuit, come back to that. Again, this is half of the E. Now there will be a voltage across that, but because we measure from plus minus, you're going to see a negative voltage, isn't it? So V out will be a negative 50 volt there. Okay, here you're going to have 50 volt. This is 50 volt, half of the E, right? And that's why here you're going to have minus half of the voltage, right? So it's very clear to be able for you to get the output voltage, a square output voltage. So now if you look at the output voltage, it will be a square waveform, isn't it? So you have to relate with the harmonics of the square current. Remember, okay, remember square waveform, you always have a fundamental. What else? The third, the fifth, seventh, which is the all odd harmonics, isn't it? Yeah, for square waveform, so you're going to have first, third, fifth, fifth, seventh, and the rest, all the odd harmonics. And the amplitude of the fundamental will be, or I can write here, Cn equals to, sorry, no, it's not fundamental. For these harmonics, we're going to have 4 IDC over n pi, isn't it? It is modulus on the positive value, magnitude of 4 IDC over n pi. So if n is 1 or 3, 5, you just replace that, then you can get the amplitude of this harmonic spectrum, right? So that is a square waveform, and therefore there you are. The load voltage is a square wave and having significant low order harmonic. So very high low order harmonic, 357 components as shown below, is not favorable because the low harmonics component require a large LC to filter out the components. So you need to have a very large capacitor, LC capacitor, low pass filter to remove all of this. Remember, if you're able to remove this by using low pass filter, you will see after the low pass filter, then your output will be only consist of fundamental, isn't it? So fundamental, you're going to see a sinusoidal waveform. And so that's why we need the filter to remove all the harmonics here. But again, because it's very high, you're going to have a very high L and C. So the component L and C will be very high capacitor, and so it's not favorable. It's not usually used. Okay, so that is square waveform. So you can think the same for quasi square waveform, isn't it? So we know that the quasi square waveform always have this. We just give you a recall. So this is your quasi square waveform, isn't it? That we learned during the rectifier. So here you have 30 degree, and then 150 degree, then you have 210, and you have 330 degree there. And the pulse, we're going to have a 120 degree pulse. This one also 120 degree pulse, isn't it? So you need to switch on S1 from 30 to 150 degree, and then you're going to switch turn on switch 2 for 210 and 330 degrees. So that's why the gate signals here from 30 to 150 degree, and you have 210 to 310. And the circuit operation is similar to what we have just now. Okay, and let's look at the waveform again. There you are. So whenever switch 1 is on, you're going to see that the output across VR will be half of the positive, so positive, and then during S2 is on, you're going to have negative half E across the output, right? So therefore your output voltage is a quasi square waveform, isn't it? Quasi square waveform, right? Just easy as that, right? And then therefore this is your amplitude again. So in this case, let's look at the fundamental again. So this is quasi square waveform. So Cn, you still remember? So Cn equals to 4IDC over n pi cos n pi over 6, isn't it? Right? This is for the rectifier. So here, in this example, you need to replace that IDC with, look at your square waveform, quasi square waveform just now. It is half, isn't it? Half of E. Before this, in the rectifier, when we discuss the rectifier, your amplitude here is IDC, isn't it? The output current. So here, in this inverter, you're going to replace that with whatever the amplitude here. So in this case, you're going to replace with half of E, just as that. And similar to the square waveform just now. For square waveform just now, you have Cn equals to 4 IDC over n pi. So now you're going to replace that with half of the E. Okay? So this is square waveform, and this is for quasi square waveform. Right? Okay, so you can calculate what will be the fundamental here. Okay, by replacing the value of n. Remember, for quasi square waveform, we don't have triplet harmonics, isn't it? It is odd, but no triplet harmonics. No triplet harmonics. So that's why you don't see third, you don't see ninth harmonics. It only consists of fifth, seventh, and the rest. Right? So again, if you have a low pass filter, you can remove this, and therefore only left the what you call it, so fundamental. And so fundamental, the output will see only a sinusoidal AC waveform. Right? So that is quasi square waveform. And again, this scheme, this control technique also can be applied to full bridge. We're not going to show here the full bridge. So for full bridge, you just think of this. So you're going to connect this with, you're going to connect with another switch here, another switch here, isn't it? Okay. So you're going to add switch 3 and switch 4 here. So these two will going to have the same pulse. The diagonal switch will have the same pulse. So if I can redraw, so this will be S1 as well as S4. Okay, and then for another switch, we're going to have S2 and S3 from 180 degree to 360 degrees, so here from 0 to 180 degree. Okay, so the diagonal switches will receive the same pulse, right? Receive the same pulse. So whenever S1 and S2 so whenever S1 and S2 on, so sorry, S1 and S3, so I'm going to put that S3, S2 and S4 will be off. Sorry, this is S4. Sorry for that. I say this is S4. So whenever S1 and S4 on, so this is on, this is on, so it will appear as a short circuit, isn't it? So it will appear a short circuit here. and S3 and S2 will be off. Okay, so now your current, the equivalent circuit will be from E, input voltage, through S1, and then load, then short circuit again, S2 come back to S4 come back to negative. So this is S1, this is S4 short circuit because it is turned on, and therefore the output voltage will be equals to, this is E, this is also E, isn't it? So the output voltage will consist of square waveform. Only the amplitude will change from half of the E before for half bridge. For full bridge, you're going to see E, yeah, wherever the input voltage is. So the amplitude will be equals to the input voltage. Only that. And quasi square waveform for a full bridge will be the same explanation. So this is your S4. So this is S2. Right? So whenever S1 on, S4 on, S2 will be off, S3, this is S3. S3 off, this is also off. And therefore, your output voltage will be quasi square waveform, and this will be E3 plus E, and this is minus E. Okay? So the output voltage always in the form of E and input voltage, and wherever S1 on, so it will be positive. Whenever S2 and S3 on, will be negative. It is always in the form of E. It will fluctuate from E and E, or half for half bridge, half E to minus half E. In this topology, very simple. All right, so that is a full bridge, so it also can be applied. And finally, you're going to have this the third operation. And by the way, for the quasi square waveform, it is also known as a phase operations. Okay, it is also named as a phase operations. Right? Okay, I don't want to elaborate more. So this is also known as phase operation. The magnitude of the fundamental is reduced. Okay, however, if you look at the fundamental, it is reduced compared to the voltage waveform just now, square wave, isn't it? For square wave here is 60 plus, 60 something, and for the quasi, the amplitude is not, it doesn't reach 60 volt, and the fundamental is reduced. However, if you look at the harmonics, it is lower harmonics, isn't it? If you measure, it's a lower harmonics compared to the square waveform. So this is better. We can say that the output voltage here is better than the square waveform. So you can remove this. You can remove this and just leave the fundamental. Okay, the technique number 3, the third technique is by using the SPWM, sinusoidal pulse width modulation. Okay, so the sinusoidal pulse width simulations, again, you have learned this during your communications when we have this data, digital, we talk about digital, can't remember, amplitude modulation, frequency modulations, and we also have the data modulation, digital modulation, I can remember. Okay, so you will learn this during, you have learned this during the communication subject, where we have the pulse width modulation. So the first technique, we're going to look into the unipolar PWM with a half bridge. Okay, unipolar PWM. There will be two form of control technique, the PWM types. The first one is unipolar, the second one will be bipolar PWM. We're going to discuss this later on. I'm going to show what is a unipolar PWM. So how to produce this unipolar PWM. Okay, so just focus on this circuit. Let's see, we have this comparator, isn't it? This is comparator, and if you look at this PSIM circuit, this is a triangular signals, and we have the sinusoidal signals here. Okay, to produce the pulse width modulated signals, what you need to do is you're going to compare, so pulse width sinusoidal, sinusoidal pulse width modulation. You're going to compare a sinusoidal modulating signal, and this is normally 50 Hz frequency, and then you're going to compare with the high frequency triangular carrier signals. So you're going to compare with a, sorry for that, you're going to compare with a triangular carrier signal. Okay, you're going to compare with a triangular carrier signal. So these triangular carrier signals, we call this as a VC. Okay, VCT. The frequency will be very high frequency. Okay? For example, 2 kHz frequency compared to the modulating signal. So this is right. This is known as a modulating signals. The sinusoidal modulating signals with 50 Hz. You compare with a triangular carrier signal. So C stands for carrier signal with high frequency. It depends 2 kHz here. So in this case, you have 2 kHz. They compare with 50. So whenever the Vm greater than Vc, whenever the modulating signals greater than the carrier signals, it will produce a pulse of 1. Okay, otherwise if Vm lower than Vc, pulse is 0. Okay, remember you have this comparator, isn't it? You compare Vm with Vc. Okay, so the output of here will follow these two rules. Okay, you will follow these two rules. Whenever Vm greater than Vc, you're going to have the out pulse will equals to 1. If Vm lower than Vc, you will produce a 0. Okay, so it's on, off, on, off, on, off. So here, if you can see, during this time from 0 to this point, will be 0, isn't it? Okay, the output of the comparator will be 0. And from this point to this point, you're going to see that the output of the pulse of the comparator will be 1. Okay, and then again here you have a very small portions here. You have Vm lower than Vc, so you'll be off again for that point, for that range, and then you'll be on for that range. Okay, so it will have the same switching frequency, but the pulse will be different. Right? The duration of the pulse will be different from one cycle to another cycles. Okay? The frequency is still 2 kHz. The frequency of the modulated signals will be 2 kHz, but the signals is no longer constant value, isn't it? For example, for square wave, you always have the duration of 0 to 180 degrees, isn't it? And then the next one, you're going to have 180 degree to 360 degree. So it is always consistent. The pulse is always the duty ratio of pulse is always 50 degree to 50 degree, 50% and 50% here, is it? But for the pulse width, you're going to have a different pulse for each cycle. It can be that, is it? Okay, it will be a different pulse. Okay, for each cycle of the output voltage 2 kHz. Right? So this is SPWM switching scheme. So you can refer to. So again, whenever switch 1 is on, it is always connected to the this is half bridge, so it will be half of the input voltage. So whenever I switch one on, output will always equals to half of the E. Whenever switch 2 is on, the output will be equals to negative E. That's the fundamental, and you always to remember this is fundamental. Okay, so for the half bridge and unipolar PWM, sorry, unipolar, I've made a mistake. For unipolar PWM, you're going to compare the sinusoidal signals. Ignore that. I made a mistake just now. For unipolar PWM, you're going to compare sinusoidal PWM with a triangular carrier signals, but only consists of positive value. Just now I put the positive and negative, isn't it? That's wrong. That is bipolar. And for unipolar, you're going to have this type of triangular carrier signals. It consists only positive value. There is no negative. Just now, I just simply, okay, just now I have this waveform, isn't it? Positive and negative triangle, isn't it? That is for bipolar PWM, right? For unipolar PWM, you only have this positive value of triangular carrier signals. Okay, and then there are two comparators to produce the unipolar PWM. You're going to have two comparators. So the first one will have this from these signals, okay, and for the other comparator, for this comparator, you're going to compare with the same triangular carrier signals, but your modulating signals will be the mirror image of the first comparator. Yeah? So your modulating signals now will be the mirror image of the first comparator. That is a different, right? It's a different. So this will be the comparator number 1. Okay, and this is comparator number 2. Right? And therefore you still have the same triangular carrier signals with positive value only. Is that right? So in this case, you can see that whenever Vm greater than Vc, so you're going to have a pulse from there to there, for example. Is that right? There from there, off, there, and next you will be off all the way. Is that right? Yeah, you will be off all the way to 360 degree because Vm is always below than the modulating signal is always below than the carrier signal, so it's always 0 here. And that's all for the comparator number 2. For the first half, it will be 0 because Vm is lower than Vc, and after the half cycles, then you have the pulse for this. Right? So that signals, that PWM will be fed to S1, and these signals will be fed to S2. Right. So again, whenever S1 on, the output will be equals to half of the input voltage because of a half bridge. Whenever S2 is on, the output will be equals to negative half of the input voltage. So that will be the operating principle. So let's look at the waveform. That is a clearer waveform. Look at the waveform. Okay, so remember this is sinusoidal signals. Here the frequency is 2 kilohertz. All right, look at this. The input is 100 volt, and the modulation index is 1. So what is a modulation index? Modulation index is the ratio between modulating signals and your carrier signals. Okay, so what is Vm? And this is Vc. Okay, so modulation index is the ratio Vm, the amplitude of Vm equals to divided by Vc, the amplitude, isn't it, with a hat. So in this case, the modulation is 1 because you can see that Vm equals to V peak M equals to V peak C, isn't it? So that's why modulation index is 1. And the output frequency will be the switching frequency will be 2 kilohertz, and your modulating signals will be 50 hertz as usual. So that will be the output of the comparator, which will be the signals, the control signals to your switch. So in this case, switch 1 will only on whenever you have a pulse of 1. Okay, so switch 1 will be on from there, on that pulse, and then be off, on, off, on, off, on, off, on subsequently. So it will depend on the pulse from the comparator 1. And for the switch 2, so this will be fed to switch 1 and this will be fed to switch 2. Is that it? So this is S2 on. So therefore you can imagine the output will be what? In this case, your output will be equals to half E, positive half E across the load, and during this S2 is on, the output will be negative half of the E, and it will follow exactly as the modulated signals. Is it? I hope you can imagine that, and therefore I can show you the output voltage here. So in this case, this will be the output voltage. Is it? So this is during S1 is on, and this is during S2 is on, and it will connect to half of the E, and it will be connected, plus half of the E, and this will be negative half of the E voltage. In this case, because the input voltage is 100, so the output become 50 hertz, 50 volt. It will be connected to 50 volt. So all of those, this is your output voltage. Of course, if you look closely, it doesn't, with your eyes you cannot see any benefit of having this PWM waveform, isn't it? It's not square waveform, it's not quasi square waveform, isn't it? It's a pulse of the plus minus, but the beauty is the beauty of why PWM is very, very famous in PWM inverter, because if you look at the harmonics, right, when you look at the harmonics of this waveform, then you see that it consists of fundamental, okay, perform the first Fourier transform, Fourier analysis, do the Fourier analysis. It consists of fundamental component, and this fundamental component can be calculated using this equation. Whatever the modulation index is, and multiplied by the amplitude of your pulse here. So here half of the E, because this is half bridge, isn't it? And because this is half bridge, so modulation index multiplied by half of the in, therefore the output will be equal, the fundamental will be equals to 50 volt. And if you look closely, there is no significant harmonics. There is no low order harmonics. No low order harmonics. There is no third, fifth, 7, 11, 9, 11. There is no low order harmonic. The next order harmonics exists at switching frequency. Look at that. Our frequency is 2 kilohertz, isn't it? Okay, you can ignore this. This is something else. You can ignore that, right? Because you see that the next harmonics actually centered around 2 kilohertz here. there is no component at 2 kilohertz, right? There's no component at 2 kilohertz, but there is a harmonics around the switching frequency and its multiple, isn't it? 2, 4, look at this, okay? I can show you. It only exists at 2 kilohertz and then 4 kilohertz and 6 kilohertz. That's the only harmonics exist for the quasi square, the pulse width modulation modulated signals. Okay, so on. The characteristic of the harmonic. So the characteristic of the harmonic spectrum will be fundamental. Okay, we can see that this is fundamental. No low order harmonics. There's no 3, 3rd, 5th, 7th as we observe for the square and quasi square waveform. And the only harmonics around, we put it around because there is no harmonics at the switching frequency. It is around switching frequency and its multiple. Its multiple will be 2, 4, 6. Isn't it? If your switching frequency is 1 kilohertz, then it will be 1, 2, 3, 4, 5. If your switching frequency is 4 kilohertz, then it will be 4 kilohertz. Next will be 8 kilohertz and the multiple. It's multiple. So the quality of waveform generated using Pwm is much better than quasi-square output where no low order harmonics current present in the waveform as shown above. It is much easier to remove the high frequency component using small size of LC filter. So the same story, the same theory. If you can remove this, right, then you will be able, the output will only consist only the fundamental, isn't it? And it is easy, and the LC, the low pass filter, will be much lower if you want to, if the harmonics at high frequency. That's high frequency compared to just now we have third, which is 150 hertz. Now we only remove to 2 kilohertz, so there will be your LC filter will be low size. It will be smaller size, and it's easier for you to remove the battery. I can show you the PSIM later on. Okay, so this is half bridge with a PWM. So you can think, the same principle for the full bridge, isn't it? For the full bridge, the only difference is that will be equals to E, isn't it? And minus E. In this case, you're going to have 100 volts here. This is also 100 volt. And if you look at the harmonic spectrum, that will be changed to 100 volt because now it becomes MA multiplied by V in or E. So you get 100 volt. Okay, for full bridge operation, full bridge topology circuit. Right? Okay, let's proceed with the Pwm switching. Okay, we're going to look into again full bridge topology. Just repeat it. Now we're going to explain the bipolar PWM. So unipolar we have seen just now. For unipolar, you're going to have S1, S2, S3, S4, and then you have two comparators. Okay, two comparators. In this case, we're going to have 1 kilohertz switching frequency, right? And this is modulation index. Because you compare modulation index is always Vm peak divided by Vc peak. So the Vc peak will be have 1 volt. The Vm will be 0.8. So here you're going to have 0.8 volt divided by 1 volt, isn't it? 0.8 volt divided by 1 volt. So your modulation index equals to 0.8. Right? So you have these two, and then again the diagonal switches will receive the same comparator signals from that first comparator, and for the other diagonals S2 and S3 will receive from the other comparator. Okay, so as I showed just now we have 0.8. Just now our modulation index is 1. So let's have a look at the waveform. So now your waveform is, if I can zoom it a bit, Okay, so now you're going to have this is 1 and your modulating signals will be 0.8. Okay, yeah, okay, 0.8 and this is 1. So if you compare, the modulation index is 1, modulation index is 0.8, so that's why it's 0.8. So that would be the modulating signals, modulated signals. Okay, so this will be supplied to S1 and S4, and this will be connected to S2 as well as S3. Okay, and therefore you're going to have output voltage equals to that. Okay, because this is a full bridge, then become 100 volt and minus 100 volt. And if you look at the harmonic spectrum, that become 80 volt because your modulation index is 0.8 and your full bridge then it become 100, and therefore your the fundamental will be 80 volt. So now look at the harmonics. So it will located at the switching frequency and its multiple 1 2 3 4. Is that it? And if there is no component at the switching frequency, no component, it only is around the switching frequency. Yes, around the switching frequency. So this is characteristic of the unipolar PWM. Okay, and for bipolar PWM, look closely. For bipolar PWM, you only have one comparator. Okay, only one comparator. So what you're going to do is, again, you're going to compare with the modulating signals with a triangular carrier signals, but now your triangular carrier signals will consist of positive and negative values. So sorry for that. So it will be this. Okay, so it will consist of positive and negative values. Is it? So again, whenever the output is whenever Vm greater than Vc, it will produce 1. Whenever Vm lower than Vc, it will be 0. So here you're going to have there from there to be on. Here you're going to have off, then off again, then be on there, the rest. Here you be off, that. Okay, proceed. Okay, so this will be connected to so this waveform will be to S1 and S4. Look at that, the output will be connected to S1 and S4. Okay, the inverting version, the mirror image of these modulated signals, which is here you're going to have the inverting version. Whenever this is on, off, it will be on. Whenever this is on, it will be off, isn't it? So the inverting version of this PWM modulated signals, this will be supplied to S3 and S2. Yeah, look at this. So here you have inverter equivalence. It's it will invert. So this component will invert whatever the value comes from. If 0, it will produce 1. If this is 1, it will produce a 0, the inverting version of that. So therefore, this will be connected to S2 as well as S3 here. Okay, so if you look at the signals now, there you are, right? So you have the comparator. You compare the modulating signals with triangular carrier signals, and that produces the SPWM1, and the inverting version of VPWM1 will be connected to S2 and S3. So here you're going to have S1 and S4, this will be connected to S2 and S3, right? So again, similar output voltage. Wherever S1 is on, whenever S1 and S4 is on, the output will be connected to the positive E, positive or positive V in. Okay, whenever S2 and S3 is on, it will be connected to the negative E, which is negative V in. Okay, just that. Right? So therefore, if you look at the output voltage now, it will consist of this waveform. Compared to just now, if you look at the unipolar PWM, your output is sort of, if I can redraw that, okay, it will consist of this type of waveform, isn't it? And this output, isn't it? So this is bipolar PWM. Sorry, this is unipolar PWM, unipolar, and this is bipolar PWM. Different output voltage. But again, if you look at this waveform, this is again far from the sinusoidal signals, AC waveform, isn't it? But the beauty is, when you look at the harmonic spectrum behind the load voltage here, behind the PWM output voltage, bipolar PWM here. So when you look at that, there you are. You're going to see our fundamentals. Okay, this is fundamental component, and again this fundamental component can be calculated using this equation, modulation index multiplied by V in. So again, this is 0.8 multiplied by 100, so you get 80 volt. And then there is no low order harmonics, just ignore this. Okay, actually there is no low order harmonics, there is no third, fifth, seventh, there is no low order harmonics. The next harmonics actually exists at switching frequency. Now at switching frequency there is a component. Compared to the unipolar just now, there is no harmonics at the switching frequency. But for the bipolar PWM, we have the components at the switching frequency as well as the side bands. We also call this a side bands, right? The harmonics around the switching frequency, and it's only exists for, look at this, 1, 3. There is no component at the even multiple, isn't it? For even multiple, there is no component, but for the odd multiple, there is a harmonics. Let me highlight that one as well. There is no there is no harmonics for even multiple, only exists for 1, 1, 3, 5, 7, 9. That is harmonics. Okay, so the harmonic spectrum bipolar is quite similar to unipolar. However, the magnitude of the harmonic component is larger than the fundamental. This technique, however, has the disadvantages because the output jump. What it does it mean? It means is that the output voltage jump from 100 volt to minus 100 volt. So your switches will experience a large jump from 100 volt to minus 100 volt. So you just can think of what happens to you if you jump from 4th floor compared to 1st floor, isn't it? If you have a multiple story building, if you jump from the 4th floor, you will suffer a lot compared to if you jump from the 1st floor, isn't it? So that also can be happens in the switches. So here it jumped from 100 volt to minus 100 volt compared to the bipolar PWM. If you look at the bipolar PWM, okay, so it jumped from 100 volt to 0 first, isn't it? 100, 0, 100, 0, 100, 0, and then from 0 to 100, minus 100. But for the bipolar PWM, it jumps straight from 100 volt to minus 100 volt. So it will experience 200 volt of voltage change. Okay, so that is what meant by the output. So therefore impose stress on the power switching devices, because always perform switching for the whole cycle. So it imposes stress to the power switching devices. And the characteristic, if you look at the characteristic now, it consists of fundamental, no low order harmonics, the harmonics at the switching frequency and its odd multiple. Harmonics around the switching frequency and its even multiple. Forgot the even multiple here. Harmonics around the switching frequency and its even multiple. Yeah, this is even multiple. Harmonics around the switching frequency and its even multiple. Harmonics at the switching frequency and its odd multiple. So that's why you see the component at 1 kilohertz, and then 3 kilohertz, 5 kilohertz, and the rest, isn't it? But there is no harmonics at 2 kilohertz, 4 kilohertz. Right? So that is the characteristic of the harmonics. Okay. Okay, let's continue with the circuit simulation. Okay, so we're going to look at the unipolar PWM of the full bridge topology circuits. Right, so you can download from the Padlet. I share with you the circuit for the PCM, circuit for the full bridge with a unipolar technique. Right, so this is circuit. So you have two comparators. Right, you have two comparators, comparator number 1, number 2, and then look at the comparator. Okay, this comparator 1, and you compare the sinusoidal, the modulating signals, sinusoidal modulating signals. Okay, so this is, I can rename it as a modulating signal, VM, or I can just put a VM. Yeah, okay, right, so this is modulating signal, and then this is my carrier. Right, the triangular carrier signal. So the duty cycle is 0.5, V peak to peak. So what it does is, for this source, you have to understand, for this source, triangular carrier signals, it always produces this type of waveform. Okay, so if you put this a peak to peak, so this will be 1 volt, and then 0.5 duty ratio, so you will have a equal, right? So you will have a 0.5 there, 0.5 here. Okay, so you have an equal triangular signals, because sometimes you may want it to be a sawtooth signal. Some of us want to be a sawtooth, so it will be different. This can be 1 if I'm not mistaken. If you change this to 1, you will get this type of waveform. Alright, this is sawtooth type of triangular carrier signals. Okay, this also applied in power electronics, right? But in our examples here, we're going to focus on the triangular carrier signals here. So you have to make it at 0.5, 0.5. So the duty cycle 0.5, and then frequency 1 kilohertz, and then V peak to peak is 1. So you compare that with the modulating signals, and for the other comparator, the modulating signals will be the inverting version, and that's why you have phase angle of 180 degree, which means initially your comparator 1, we're going to have a normal sinusoidal signal, 0 to 180 degree, and this is 360 degree. But for the second comparator, you're going to delay by 180 degree. Okay, so you're going to delay this waveform by 180 degree. That's why you start with this kind of form. Right? So that's why you have this phase delay angle of 180 degrees. So it will delay. So therefore you have an inverting version for the comparator number 2. Right? Okay. Therefore you run it around So again, the rule of thumb for your, I come back to, okay, so rule of thumb, your switching frequency Fs is 1 kilohertz. Fs is 1 kilohertz. Therefore, the time step, okay, delta T here should be 1% of 1 over Fs, right? So the smaller the better, the waveform, the smoother the waveform. However, you have a lot of number of points, so you have to compromise between the two. Okay, so here put it as a 1 to the power or 0.1 microsecond. This is also equals to 0.1 microsecond, right? Okay, I think it's small enough, and therefore then you can run circuit. This is what you're going to obtain. And let's look at the sine wave sinusoidal modulating signals compared to triangular modulating signals. And then you have the BP SPWM1. Have a look, and there you are. Okay, so that will be your SPWM1. I can highlight, change that to black and make it clearer. That will be my SPWM1. Okay, so during negative half cycle, it will turn off because the modulating signals is always lower than the carrier signals. Okay, and what happens to the other comparator? You can just check it by line 2. Try to change it to 1 black. So that is 2, and finally your output voltage Vout Vload. Right, so this is a this is a full bridge, therefore 100 volt minus 100 volt depends on the input voltage. If the input voltage is 500 volt, so it will be 500 volt minus 500 volt, right? And from there, I can delete this. I'm going to look at the harmonic spectrum, so I must delete the other waveform and only left the output voltage. So just simply click this button, isn't it, to get the harmonic spectrum. Make sure that it at least 2 cycles displayed before you hit this button. Okay, so you must have at least 2 cycles. Then click FFT, and therefore that will be your harmonic spectrum. Change your frequency so that you can see. Okay, right. So that will be the fundamental 80 volt, and then the switching frequency and its multiple. There is no component at the switching frequency. Okay, so this is unipolar PWM. Alright, what about the bipolar PWM? Let's have a look. Okay, inverter with bipolar PWM. Again, I'm going to share with you this. So we have 0.8. Look at that. So here we can compare the modulating signals with 0.8 peak voltage, frequency of 50 Hz, compare with the triangular carrier signals with have positive and negative, isn't it? So in this case, I add this. You need to have a DC offset. So this is actually taken care by that voltage, amplitude of 1 volt. So this waveform, if you still remember, I mentioned you just now, the triangular carrier, the source here will only produce this type of waveform, isn't it? Okay, so now I minus, this is summation there. So this signal will minus 1 volt. Okay, so this is 1 volt, so it will shift down 1 volt. So there is a DC offset, so it will shift down by 100 volt. So it will produce this voltage, 100 volt, 1 volt, sorry for that. Okay, so 1 volt, and therefore you have, here is 1 volt, and this is minus 1 volt, compared to just now we have 2 volt here. So you DC offset, you move down 1 volt by 1 volt, so it will shift down to 1 volt. And then I adjust because I want to start at this frequency, at this 0. I want to start at that 0 volt, so there must be a delay, isn't it? I have to make a delay so that I start at 0 voltage. So that's why if you look at this triangular source, there is an extra phase delay there. Okay, there is an extra phase delay of 90 degree. Still the same 0.5 duty cycles. The V peak to peak is 2 volt because I want to push it down to by 1 volt. Therefore, I can get the amplitude of VC equals to 1 volt, right? So therefore, the output will be that one. Okay, this is 1 volt minus 1 volt, and you're going to compare with the modulating signals here. Yeah, so that modulating signal will be 0.8 volt. Yeah, so the modulation index equals to 0.8 volt. Okay, so I hope you understand you try to understand the PSIM circuit so that you can explore more on the circuit. Okay, so the output of that comparator will be fed to comparator 1, S1 and S4, and then the inverting version of that will be provided to S2 and S3. Okay, just that. Alright, so run the simulation again. Then let's see the SPWM, compare, put them all together. See what we do. There you are. I can remove this, remove these two. So that is a comparator. Now comparison. Okay, add another waveform, add another waveform. There you are. That is an inverting version. Better color that as a blue. Okay, so whenever Vm greater than Vc, you will produce 1, and the inverting version will be 0. Okay, so SPWM1, SPWM2. So this will be connected to S1 and S4. This will be S2 and S3. Yeah, and therefore the final version will be we load the output voltage, so it will say minus. So whenever S1 is on, so it will connect to this is when S1 and S4 on, it will connect to 100 volt, and then whenever S2 and S3 is on, it will be connected to the negative 100 volt, yeah, for full bridge. Okay, so that's why your output voltage is positive and negative of 100 volt there. Again, to get the fast Fourier transform analysis, I'm going to remove this, delete the screen, and then I'm going to do the Fourier fast Fourier analysis and change x axis, and that's what I'm going to obtain. The fundamental and then the harmonic at the switching frequency and its odd multiple 1, 3, 5, 5th, 1, 3, 5, 7 rise. But for the even harmonics, 2, 4, it will be there is no harmonic is to even multiple, right? And I'm going to show you, I did mention that if you put a filter, okay, once you put the filter, you're going to remove the harmonics, isn't it? And then you let only the fundamental to pass through to the load. Okay, so I'm going to show the low pass filter. for bipolar PWM. Okay, so this is bipolar PWM, right? We only have one comparator, so you can differentiate between bipolar and unipolar by looking at the number of comparators. If it's a single comparator, then this is bipolar PWM, right? So in this example, I'm going to show you the low pass filter by using the capacitive low pass filter. So the component only consists of this R and C and capacitor. So you add another element, which is okay, you're going to add the R here as well as the capacitor here. And how to calculate that? So FC equals to remember, low pass filter. I hope you familiar with this. So with a low pass filter, what you do is, let's say this is your fundamental, and then remember I have this 1 kilohertz switching frequency. Let's say this is a switching frequency components and the rest. So if I want to remove all of these, I'm going to design an LC filter. Okay, so I'm going to design my LC filter such that it will do this. Right, so this is my LC filter, okay, whereby if this output voltage multiplied by this LC filter, the output only give this fundamental, isn't it? Just you can think of how to do it. V out here, right? This is your V out. And then you multiply by this LC filter, low pass filter. This is low pass filter, and the output will become, so this is your component, isn't it? Harmonic. So you multiply by this, then the output only consists of fundamental, because the rest will be 0. Sorry. I make a wrong drawing. Okay, so let's do it again. So you have this VPWM, which consists of fundamental and the switching frequency harmonics, etc. And then you multiply with this low pass filter. Yes, this is low pass filter. Alright, this is, let's say this is 1 volt, this is 0 volt. Okay, so you multiply this component with the low pass filter. Of course, the output will be equals to fundamental, and the rest will goes to 0, isn't it? Yeah, because this is your fundamental, and the rest of the frequency, which is at 1 kilohertz, etc., will be multiplied by 0, so you get 0 here. So the output only the fundamental, which is positive. Right, so that's the idea. And to get the corner frequency, this is known as corner frequency. Remember, this is low pass filter, so there is a corner frequency somewhere there. So to design the corner frequency, that will be 1 over 2 pi RC. So that is a calculation how to get the FC. So if I set this frequency is equals to 1 kilohertz, because remember now it's 10 kilohertz. The switching frequency is 10 kilohertz, so I'm going to let the corner frequency at 1 kilohertz, and then I can design this, and therefore that will be 159 micro. Okay, and I have to make sure that this is very small. The resistor is very small, so that a low voltage drop there. Okay, this will be a low voltage drop. Okay, and therefore if I run this circuit, so let's look at the output before the low pass filter. So that will be the output voltage before the filter. Again, this is a typical bipolar PWM output, isn't it? On off, on off. And then if you look at the output after the low pass filter, you will see this. Look at that. It is sinusoidal, so it removes, isn't it? Sinusoidal. And of course, if you look further, it is a sinusoidal, but then there is a small high frequency component at your output, isn't it? That's good enough for your output, your load. Your load is good enough to have to receive this, happy enough to receive this output voltage. So if I can click this, look at that. So this is your VPWM, and now the output only see this low pass filter, and there is a small switching frequency at 10 kilohertz. That's why you see it's a tick, isn't it? If you look at the waveform just now, it is a ripple. There is a ripple, isn't it? Even though it's sinusoidal, but it's a ripple because of that component, 10 kilohertz component. Okay, right? So this is how you can use the low pass filter to remove the PWM waveform, and therefore your output, your load, now will see a very nice sinusoidal waveform, right? Because our target is to get the AC sinusoidal output, isn't it? All right, that's on the single phase inverter. Now we're going to look into the three-phase inverter. Okay, let's look at the three-phase inverter. Okay, as for the three-phase inverter, there will be three control technique, which is the first one will be 120-degree conduction mode, or the other name will be two simultaneously conducting devices. Number two, 180-degree conduction mode, or three simultaneously conducting devices, and the third one will be the sinusoidal PWM. So for the first method, which is the control, which is the 120-degree conduction mode, the first one is that firstly we're going to look at the circuit connections. So you're going to have the same three-phase, just like the connection of the three-phase rectifier, three-phase full bridge rectifier, whereby you're going to have switch 1, switch 3, switch 5, switch 2, switch 4, switch 6. I hope everybody by now you already memorized the sequence of the labeling of the switch, okay, which is as switch 1, switch 3, switch 5, and the bottom group you have switch 2, switch 4, switch 6, right? So always label the device in that arrangement: S1, S3, S5, S2, S4, S6. Because if you mistakenly label the sequence of the device, you're not going to have the proper 120-degree, 180-degree connection mode. And then the input will be the DC voltage, so that will be connected to the positive connections here, and then we have a negative connections there. Right? Okay, and then the output of that will be taken at the midpoint of the two MOSFET or IGBT. Okay, you'll be connected in between the midpoint of the two devices of each leg, right? So I mentioned to you we have legs. So here you have leg 1, right? Then you have leg 2, and then you have leg 3, right? So we have 3 legs, and the midpoint of each leg here will be connected to the load. So here you're going to have to connect the, so remember this will be the balance load, so every phase will have a similar R size, similar ohms, and therefore that will be connected to phase 1, and then this will be connected to the phase 2, and the third one will be connected to the phase 3. So all will be, the load will have this phase 1, phase 2, and phase 3. The polarity of the load will be in that arrangement, plus minus, plus minus, plus minus. Okay, so what is 120 degree conduction mode? You're going to let all switches here to be turned on for 120 degree and 20 degree. So all switches are here will be conducted for 120 degree. So you're going to start with so switch next one, we're going to look at this is the pulse for all switches here. So you have switch 1. That's why the labeling of the switches is very, very important. So you have this arrangement S1, S2, S3, S4, S5, S6. So this will be actually refer to the switching location. So switch 1 will be receiving 0 to 120 degree, and therefore the duration of the pulse conductions will be 120 degrees, right? And then the next switches, switch 2, switch 1, switch 2, there will be a 60 degree delay, alright, and therefore it will start at 60 degree and it will end up at 180 degree. The following switches, switch which is switch 3, will be further 60 degree delay to the previous switch 1, switch 2, and therefore it will start at 120 degree, and therefore the rest of the switches will be 60 degree delay for the previous switches that you have. So S1, S2, S3, S4, S5, S6, and this is very important, as well as the labeling of your switches just now. So it is always S1, S3, S5, S2, S4, S6. If you wrongly label the switchings here, and you will not receive the correct output voltage. Right. Okay, so let's look at the circuit operations, and let's imagine that we are at this particular point here. Okay, so let's have this region. Okay, so we start at this particular region, looking at this particular window whereby we have switch 1 on and switch 6 is on. Okay, so we're going to look at what happens to the circuit within this duration. So we have switch 1 and switch 6 is on, and the rest is off. Okay, the rest is off. Okay, so let's look at the circuit again. So we know that switch 1 is on and switch 6 is on. The rest is off, appear as an open circuit. Okay, so the current will be flowing from the source here. It will flow through that and flow into the first switch here, switch 1, and then now it goes into the load. Okay, into phase 1 load, and then it will go to there, and now it will connect to go into the phase 2 load, but in opposite direction, isn't it? Then to that into switch 6, and finally come back to the negative terminal, isn't it? Come back to the negative terminal. So only phase 1 and phase 2 will be having a voltage across it, and whereas for phase 3 there will be no voltage across the load. Right, so let's draw the equivalent circuit. So you have positive and negative, and then you start to have resistor 1, isn't it? Come back to this point, then you have resistor 1, and then you have resistor 2 there, then come back to that switch 6, and then goes to that particular. Right, so this is plus minus, and then this is also plus minus for V phase 1, then V phase 2. Okay, so now let's rearrange. So we're going to have again plus minus. This is your R phase 1, and then this is phase 2. Come back to that. So we maintain the polarity of V phase 1, and this is that point, isn't it? That point. Now you have negative positive of VP2, V phase 2. Okay, and let's assume that this is E, or 100 volt in this example, 100 volt. Therefore, we have a balanced load, so both will be having an R load, similar ohm, and therefore the voltage across it will be what? Half, isn't it? Half of E, and that also half of E. Right, so the polarity will be plus minus, and this will be plus minus. So V phase 1 will be equals to half of E. However, VP2 will be equals to negative half of E. Because it's reverse polarity, okay? Opposite polarity. Okay, so only V phase 1 and phase 2 will have a voltage across it. So let's look at the output voltage now. Right, so now V phase 1 will be half of the input, which is 50 volt, and V phase 2 will be negative half of E, which is equals to minus 50 volt here. Did it? Okay, so that is when we have this region whereby switch 1 on and switch 6 on, and it is known as two simultaneously connected devices because at any time only two switches are on, right? Only two switches are on. So this is V phase 1, V phase 2, and then V line to line. So we just look into the phase line to line voltage between V phase 1 and V phase 2. So V to line here, so equals to V phase 1 minus V phase 2. So here at this region we have V phase 1 is 50 volt minus 50 volt. So you get 50 volt. This is minus 50 volt. So 50 minus 50 volt, you get 100 volt. At this point. Okay, and next we're going to have at this point we have already discussed here. Next will be that region whereby you have switch 1 is on as well as switch 2, and the rest is off. Okay, the rest is off. Therefore, if you go back to the circuit again, you're going to see that switch 1 is on and switch 2 is on. The rest is off, off, off. So your current will flow into that, just draw it to that phase 1. Now it goes to phase 3. So there will be no voltage across phase 2. We go to phase 3, come back to switch 2, and go back to the negative terminal. So that will be the flow of current, and therefore if you look at the output voltage, there is no voltage at phase 2. Zero voltage, and we still have 50 volt for phase 1. And of course, if you observe the phase 3, there will be a negative 50 volt across phase 3, but is not displayed here. So you only have phase 1 and phase 2, and therefore for this region you have 50 minus 0, so that's why you have also 50 volts here during that point. Okay, and you can study for the rest of the cycles. So that is 120 degree, and we look at the harmonic spectrum. We're going to see that for phase 1 and phase 2 both will be having the same harmonic spectrum. Of course the amplitude will be different, but the harmonics for both phase 1 and phase 2 will be located at the same harmonics, which is fundamental. This is first. There is no triplet harmonics, no triplet harmonics, and you know at least it's a 5, 5th, 7th, 11, 13, and the rest. Okay? So there are low order harmonics. There are low order harmonics for 120 degree conduction mode. Okay, so no triplet harmonics. So that is the characteristic of the harmonic spectrum of the output voltage. And if we refer back to the voltage again, for phase 1 we have 3 levels. So this is we have 1 level, 2 level, 3 level. So this is known as 3 levels. For phase 2 also we have 3 levels, but for line to line voltage we're going to have 1, 2, 3, 4 levels. Okay? So 4 levels for line to line voltage, however 3 levels for phase voltage. So that will be the characteristic of 120 degree conduction mode. Okay, so now let's move to 180 degree conduction mode. So again, the 180 degree conduction mode tells that each of the switches here will be operated for 180 degree. 180 degree. So again, switch the same circuit connection, but the difference is the pulse, the control signals for each switches there. So instead of 120 degree, now it is extended to 180 degree conduction, but we still have the 60 degree delay. The same approach, we have 60 degree delay for each switches, and then the duration is 180 degree. And therefore, if you want to look at the circuit operations, you just simply take we just refer to one particular region. For example, here, right? So you have, if you look carefully, switch 1 is on, what else? Switch 5 is on, and switch 6 is on. So there are 3 switches are on. 3 switches are on at the same time. So that's why the name also 3 switches simultaneously conducting device. 3 switches are on with the 180 degree conduction mode. You see that 3 switches are on at the same time. Okay, so switch 1, switch 5, and switch 6. So let's look at the circuit again. So we have switch 1 on, switch 5 is on, as well as switch 6 is on, and the rest will be off. Okay, so therefore the current again will flow through from the source, and it will go to the switch 1, and there will be another current that flow through switch 5 this time. So goes to switch 1, divided into switch 1 and switch 5, and then it will flow to the output. It goes to phase 1 into that junction, and as for this side, it will go to phase 3, and then we'll go into that junction and combine together, and then it will pass through the phase 2 resistor, then come back to switch 6, and then go back to the negative terminal. So that is when we have switch 1, switch 5, and switch 6 are on during that region. Okay, so now we try to draw the equivalent circuit. Therefore, you have now the input voltage, then you have phase 1 there, and then it's splitted actually. It's splitted into two, resistor 1 and resistor 3. Okay, so it is not only goes to switch 1, resistor 1, but also resistor, sorry, this is just write the voltage. So here you have V phase 1 as well as V phase 3. Is that it? So it will separate into divided of two resistor, and then this junction, and they will cross over the VP2, and now it is negative positive. Is so this is positive negative. So now here in the equivalent circuit you have negative positive of V phase 2, then come back to that particular area. Is so each have the same resistance R. So how to get the voltage across V phase 1 and V phase 3 and V phase 2? So you have to, of course, get the total resistance. This is a parallel connection, and so you need to get the total resistance across this V phase 1 and V phase 2, and then we need to do the voltage divider rule, isn't it? Okay, so I'm going to redraw that again so that we do just simply plus minus here, which is the voltage phase for 1 and 3, but now resistor become reduced to what? Half of R, isn't it? Because there are two parallels, so it become half of the R, and this is R, but now plus minus plus V phase 2, isn't it? Okay, clear? So now to get the voltage across both resistor, here you need to do the voltage divider rule, VDR, voltage divider rule. So for voltage VP1 and 3, so you have half of the R divided by half of R plus R multiplied by V in or E, because we use E just to maintain the E, and therefore if you solve that, then you get what? 1 over 3, isn't it? Okay, 1 over 3 of E. Okay, so in this case, if you have 100 volt, then that will be 33.33. Okay, 33.33. So for V phase 2, it become R, half R plus R over E. So if you solve this, you get 2 over 3 E, and it becomes 66.67 volt across phase 2. Phase 2. So if you, negative, sorry, this is negative voltage, right? So it's a negative voltage. So I hope you don't get confused. This is plus minus, and then here also plus minus 66.67. This is 33.33. Okay, so that's why VP2 will see negative 66.67, and this is positive 33.33. Right? So phase 1 and phase 3. Phase 1 and phase 3 will see this 33 will be having this 33.3 volt, but across the phase 2 it will have the negative 66.67 volt. Right? Understand? Okay, so let's look at the waveform. That will be the voltage. Okay, we look at this particular region, isn't it? So phase 1 is 33.3 plus 33.33 volt, but for phase 2 you have negative 66.67 volt. That. Right? And again, V line to line equals to V phase 1 minus V phase 2. So that's why we have 33.33 minus 66.67, you get back to 100 volt there. So please understand, continue with others sequence until you get the whole cycles there, and look at the line to line voltage and phase voltage, and you can observe that for 180 degree conduction mode, you're going to see that there will be 1, 2, 3, 4 levels, 4 levels for phase voltage, but 3 levels for line to line voltage. It's opposite to the 120 degree conduction mode, right? It's opposite. And when you look at the harmonic, you see the same, you observe the same pattern, whereby you have fundamental, no triplet harmonics, right? But you have a harmonics at 5th, 7th, 9th, 11th, 13th, the rest. Similar harmonics content for V phase to phase and V phase and V line to line. Alright. The above will also show that no triplet harmonic present. Same set conduction mode is better than. Okay, so that is about the 120 degree and 180 degree conduction mode. Now we're going to look at the last technique, which is the pulse width modulations. So previously for single phase inverter, we have unipolar Pwm and as well as bipolar Pwm, isn't it? Right, we have unipolar and bipolar Pwm. So for unipolar Pwm, you're going to compare between modulating sinusoidal modulating signals with the triangular, the positive part, positive only triangular carrier signals, isn't it? Okay. But for bipolar Pwm, you're going to compare between the modulating signals, sinusoidal modulating signals, with the triangular carrier signal, but it has a positive and negative. That is bipolar Pwm. So for three-phase inverter, what you're going to do is you're going to compare the three-phase supply voltage, three-phase voltage, right? So I hope you still remember how to draw the three-phase waveform. You draw a dotted line there, then draw the triangles, isn't it? You must remember how to. You must know how to draw the three-phase voltage, right? Extend to the negative circle. So then you connect the tips of the triangles there. Okay, then you make it bold. So this is red voltage. So that is red, and then yellow voltage again. This is yellow, red, yellow. Sorry for that. Oh, yellow and blue. Okay, so you have red, yellow, and blue compared with a single carrier signals. Look at that. This is a carrier signals, and then you have this supply, three-phase supply voltage, three-phase voltages, and you compare with a single carrier signal. So now this will be your carrier signals. So that will be the carrier signals. Okay, depend on the frequency. It depend on the frequency. Okay. Sorry for that. So there's a triangle, and the modulation index still the same definition. We have the same definition, which is Vm peak divided by Vc peak. So that will define the Vc peak, and the modulating signals here will define the Vm, the peak of the Vm there. Right? So you compare between those signals, and the output of that, look at this. For comparator red, the first one, red comparator here, output of that will be connected to the first leg, isn't it? This is the first leg, switch 1 and switch 4. So the output of the comparator will go to switch 1, and the inverting version of that pulse will be connected to S4. Right? So you have to understand the how to construct this sinusoidal pulse width variation for three-phase inverter. So the question will ask you show how the three-phase inverter can be obtained by using the sinusoidal pulse width modulation. So you have to draw all the circuits, label correct labeling, and then you also have to show the circuit connection as well as the waveforms. Yeah, how you compare and to produce the signals, and then the inverting version here, and then you must explain the circuit operation. Okay, so switch 4, and for yellow phase, the output of that will be connected to top bot switch, and the inverting version of the pulse will be connected to the bottom group of switches. Okay, so this will become V red, V yellow, so as V blue there, red, yellow, blue. So that will be the output. Okay, and that's and I'm going to show you the simulation, right? To show the simulation. So if I can have the alright, so that is the simulation. Okay, so this is the supply. I can have a single, or you can have a block set there. So now I have a single sinusoidal signals with 120 according to the delay, minus 240 degree for yellow phase, and then simulate that. Then you see the VPWR, so that will be the PWMR, the red phase voltage. The PWM output of the comparator, for R. And then let's look at the V phase R. So this is the output voltage for phase red phase. Look at that. Yeah. So this is the output voltage for red phase voltage. Okay. Look at that. This is simulation again. This is phase voltage, is line voltage there. Okay, phase voltage, line voltage. And then if you look at the harmonics, this is what you're going to obtain. Similar pattern, similar trend, V line to line. So in this PWM, there will be fundamental, no low order harmonics, as we did before. No low order harmonics. The next harmonics is actually at the switching frequency. So the switching frequency here is, if I'm not mistaken, is 1.5 kilohertz. It's a 1.5 kilohertz. Look at that, 1.53 kilohertz. Yeah. So this is harmonics. The above therefore show that no low order harmonics present in the upper voltage is better than. However, the magnitude of the quantum is lower than the above mentioned two conduction modes. In practice, the higher frequency components can be easily removed by installing a low pass filter. So I can show you the low pass version. Okay. Do I have that? Let's look. No. There you are. Okay. So here, same as we did just now. This is a low pass filter. Again, with the same carrier frequency of 10 kilohertz, which is 10 kilohertz, and then the same L and C size value. Just put on the first red phase voltage. Maybe just look at the phase R phase, we just apply the LC across the phase 1. So let's have a look what happens. Transmission. Okay, load unfiltered across R. So what happens? Okay, so this is the load across the before the filter, and then V load filtered. So there is the voltage after the filter. So you have a nice sinusoidal signals after you put in the filter. Okay, so this is the advantage of using that PWM compared to the previous 220-degree and 180-degree conduction mode. Okay, I think that's it. We're going to continue on the later on the detail how to produce that pulse with modulations with controller. If we have a controller, then how to produce that PWM um, to be fed to the switches. Okay, thank you so much.